Good morning. We're going to be looking at 3.2. It's the mean value theorem and Rolle's theorem. So let's get to it. It's going to be fun. You're going to enjoy it. Get yourself a cup of tea and give it a try. What Rolle's theorem says, it says, first of all, it starts off with the hypotheses, and there's three. F is continuous on a closed interval, A to B. We've seen that before, right? The extreme value theorem also had that condition. Number two, F is differentiable on an open interval, A to B. And then also F at A equals F at B. And so then there is a number C in A to B such that F prime of C, so the derivative at C, is equal to 0. So it's saying someplace in between A and B, the derivative is equal to 0. And so these pictures came from your textbook, and I think they really kind of go to show you what's going on. And so the first part of the theorem is that it has to be a closed interval and continuous. So here is between A and B. So here is just a horizontal line from A to B. It's closed, it's continuous, it's differentiable, right? Because if you take the derivative of this at any place along here, at every spot, between A and B, not at the endpoints, but at any place in the interval, you're going to get 0, right? The derivative of because horizontal, right? So, and so it says that, and F of A equals F of B, so the height, right, the y value for A, F at A and F at B are the same. And so, and then they say that someplace in between the derivative is 0. And in fact, every place in between it is 0. So they show 2 spots, but I think really on this one it's infinitely many spots. Okay, so here's another one. This one's a little you have a function that's continuous from on a closed interval A to B. It's differentiable because it's just a smooth curve. Maybe it's a polynomial curve, maybe it's a sine curve, I'm not sure, a cosine curve, but it's differentiable because it's smooth. There's no, places where things are not differentiable are where you have a corner, where you have a cusp, where you have discontinuity. So I don't have any of those kind of things. So it's just a smooth curve. So, and F at A is equal to F at B. See how the heights are the same? So it says that somewhere in between, at least one place in between, the derivative is equal to 0. And so, and when you kind of think of it, is if you kind of went up, you're going to have to come back down. And that place where you kind of come back down is a place where the derivative is equal to 0. And same here, right? F of A and F of B are equal to one another. The height of A and the height of B are equal to one another. You got, again, this smooth continuous curve. Smooth means it's differentiable there. And here's a place where the derivative is 0. Here's a place where the derivative is 0. And so just another example that they're trying to show you with some pictures that maybe look different from one another, and that's someplace where the derivative is 0 in between. And then I like to give an example in words, and this is my example in words. If I toss a ball straight up, and it goes up and then it comes down, and I catch it. So just so that you kind of envision the thing. I know this is not a ball, this is my eraser, but if I'm able to take my eraser and I throw it straight up, and it comes straight back down and lands on my hand, then if I'm letting my function be the height of the ball at any time, so you know how they had S equals F at T, and that's being the height of the ball at any time, as it goes up and it goes back down, right? And I'm pretending like I was to throw it, but anyway, when you take the derivative is the velocity, right? And we're saying that someplace, if you throw this up and it goes up and comes right back down, that someplace the velocity is 0. and you know where the velocity is 0, right at the top. And so that's all that Rolle's theorem is saying. Okay, so it says for Rolle's theorem, verify the conditions are met and then use it. So the first condition is that it's continuous. And this is a polynomial. X to the second is a polynomial term. X is a polynomial term. 2x is a polynomial term. 3x to the third is a polynomial term. And polynomial terms are continuous on their domain, which is all real numbers. And so in this case, we're having the closed interval from from half to 2. And so, so this is just a polynomial term, and it's continuous on this closed interval. This is a rational function, right? And it's continuous everywhere except for where the denominator is equal to 0, which is at 0, which is not in this interval. And so I'm just going to say this. F of x equals x plus 1 over x is continuous except at x equals 0, which is not in the closed interval half to 2. So it's continuous on half to 2. So I'm just wanting to make sure that everyone knows that I know. So I'm telling you where the discontinuity is. There is a discontinuity, and so otherwise it's continuous. Okay, and then I want to convince you that it's differentiable, and so I know that a polynomial is differentiable, right, everywhere, and 1 over x is differentiable except for at x is 0, right? And so because that's where it has its discontinuity, but otherwise it's smooth. And so this is differentiable except at x equals 0. So it's differentiable from half, and that's open, to 2, certainly. Then I have to verify that f at half equals f at 2. And these are not formal proofs, and some people have you be more than just verify. And so they're just, all they're really wanting is for you to think about it and say, you know, hey, this is a polynomial, it's continuous and differentiable everywhere. This is a rational, it's continuous and differentiable everywhere except for the where the denominator is 0, right? And that's not in my interval. So these two are met. Now I have to make sure that this is met. So this would be half plus 1 over, right? I'm replacing. I'm going to do that. I'm going to write my parentheses in here. I haven't done that in a while, right? Here plus 1 over here equals, and then this is going to be this plus this over this. And so I'm putting the parentheses in there just to make sure. I don't know if I have a nice colored pen. I was going to get one at the Target the other day. I know, it's amazing that I went out of my house. Okay, and you can put that in your calculator if you like. Half plus 1 over 1/2. Now I know that 1 over 1/2, this is 1 divided by half, which is same as 1 times 2, which is 2. So this is, so doing it by hand, you can do it by your calculator as well. This is 2.5, right? And this side over here, we're plugging in 2. And you can see, well, you're going to get the same thing, right? Because this is 2 plus half, which is 2.5. And so, yep, they're equal to one another. So all three of these conditions are met. Now we're going to apply the theorem. And I'm going to be out of room, so I'm going to apply the theorem right here. And the then of the theorem. So this was if these three things are true, then f prime of c equals 0 somewhere in the interval half to 2. So somewhere between half and 2, not at half and not at 2, not at the endpoint, but somewhere in between, half and 2, the derivative is equal to 0. So let's find the derivative here. So this is f at x equals x plus, I don't want to use the quotient rule here, so I'm going to write this as x to the negative 1. And so then when I take the derivative, I'm going to get the derivative of x is 1, and then this negative 1 is going to come down in the front, right? So negative 1, x, and then I'm going to take away 1. So negative 1, take away 1 is negative 2. So the derivative, and I want to evaluate that at c, so I'm going to put in c here. So this is 1 minus 1c to the negative 2 equals 0, which to solve it would maybe be better for me if I wrote this as 1 minus 1 over c to the second, right? And I want to solve for c. Your choice on how you solve for c. Do you add the 1 or subtract the 1 to the other side, or add the 1 over c to the other side and then cross multiply? It's your choice. Or do you multiply by c squared to clear the fraction? There's choices. I think I will add 1 over c squared. So I get 1 equals, so this was negative, so it's going to be positive over there, 1 over c squared. And then I think I am going to cross multiply to crisscross applesauce, right? So this is 1c squared equals 1. So c squared, I was going to take the square root of both sides. I think I'm getting c equals plus or minus 1, right? Taking the square root of this and the square root of that. Don't forget the plus or minus when you do that. Remember that we're only interested in the interval half to 2, so really c is 1, and I want to show you what we found. Okay, so this is the graph of f of x equals x plus 1 over x. So this is what the graph looks like, and you can see that it's certainly continuous. Here is 1, and here is half, and you can certainly see. And then this is up here at half, right? And here at 2. You can certainly see that it's continuous on this closed interval right here. So that was condition 1. You can see that this is a smooth curve, right? So that was condition 2. It's differentiable on the open interval. And then 3, you can certainly see that the height of f of half and the height of f at 2 are equal to one another. Okay, so they're saying that somewhere in between the derivative is going to be equal to 0, and so that means the slope of the tangent line is going to be equal to 0, and we found that that's going to happen at c is 1. And so right here at c is 1, you can certainly see that the tangent line is equal to 0. Sometimes they ask you to draw the secant line, and the tangent line, they're asking you to connect these, right? And asking you to draw that. And so if they ask you to do that, you certainly can do that, no worries, right? I'm grabbing a ruler because I like to, if I'm going to draw something, I like to draw a ruler. And so both of these things have slope 0, right? And so there was my secant line, and here is my tangent line. And so here's the secant line, and here's the tangent line. They didn't ask me to draw it here, but if they had asked me to draw it, I could certainly draw it on there. Then this is the mean value theorem, and it goes a little further than Rolle's theorem. And so the mean value theorem has the following hypotheses have to be met. F has to be continuous on a closed interval, a to b, so that's same as Rolle's theorem. And f has to be differentiable on the open interval a to b. Then, so this is the if these two things are true, then this is true. There is a number c in a to b such that the slope of the tangent line, right, because that's the derivative, right, so the slope of the tangent line equals, and then over here, I don't know if you guys recognize what that is, but that's the slope of the secant line. So in words, from some x equals c, the slope of the tangent line is the same as the slope of the secant line. So the slope of the tangent line and the slope of the secant line are the same. And I think that these pictures came out of your book, are really nice. And so you notice that this is my curve, and my curve is continuous on a closed interval from A to B. And I think these pictures came out of your book anyway. And also this curve is differentiable, meaning that doesn't have any corners, it doesn't have any asymptotes, it doesn't have any discontinuities, any cusps, any of those kind of things, any funny stuff going on. And then right here is the slope of the secant line. There's the slope, there's the secant line, and you can see that it's slope, right? Rise over the run. And they're saying, so this would be parallel, right? The tangent line here would be parallel. And so they're saying somewhere in between A and B, there's a place, C, where the slope of the tangent line is the same as the slope of the secant line. And there could be more than one place. And so here is another one where it's continuous on A to B, a closed interval. And so here's from A to B. And here is the secant line, the slope of the secant line. You can kind of imagine it. And here's a place where the tangent line has the same slope. And here's a place where the tangent line has the same slope. There's two places. There could be more than that. And if you think about it with a driving example, if you drive to Fresno, and if your average velocity is 62 miles per hour, so that's what you averaged on the way to Fresno, right? There would be at least one moment during the trip, during your journey, that your instantaneous velocity is 62 miles an hour. So if your average velocity is 62, so overall, and how you find your average velocity on a trip is your rate equals the distance that you've traveled divided by the time that you traveled. So if I said that I traveled 100 miles, and let's say that I said it took me 1.5 hours to do that, then my average velocity, which I called rate, but my average velocity, right, would be, I called it rate because it's what you do in algebra class, is you call it rate. 100 divided by 1.5 is equal to 66.7, right, miles per hour. Now I had given an example with 62, so I wasn't trying to match that. I was just giving you an example. And so what this would say, if I had traveled to Fresno and my average velocity, it took me an hour and a half to get there, pretend, and it was 100 miles from Bakersfield, right? My average velocity was 66.7 miles per hour. That at least one moment, my instantaneous velocity during the journey was 66.7, right? So whatever, anyway. And so that's that story. I wish I could have hit 62, but I should have planned for that, right? I should have asked you how long did it take me to get there if it's 100 miles, right? You could figure that out if my average velocity was 62 miles an hour. Something I asked my beginning algebra students. Anyway, kind of talking quietly because it's really early in the morning at my house and I don't want to disturb anyone. I hope that you can hear me though. Determine whether the mean value theorem applies to the following function, and if it does, find the find or approximate the points guaranteed to exist by the theorem and sketch the situation. So we're supposed to see, does the mean value theorem apply? So the first thing that we have to verify for the mean value, these are the ifs for the mean value theorem. Number one is that f of x is continuous. And so, yeah, it's continuous. This is just a polynomial. Yep. because f of x is a polynomial, right? And polynomials are continuous. I can even say that. Polynomials, polys are continuous. On all reals, right? And it's closed because it's negative 2 to 2. Okay, well, every polynomial is also differentiable. So yeah, f of x is differentiable on, I'm going to put this, negative 2 to 2, because f of x is a polynomial. Now, you can't say that if it's not a polynomial, but because it's a polynomial, it's continuous and differentiable on any closed interval that you have. And so that's all that those are the ifs. So here's the then, and I'm going to put a box around the then like I did before. I'm kind of a boxy person. Then that means that f prime at c equals the slope of the secant line, right? And so things I'm going to need to find, maybe I'll just find these things and list them out here and then put them in there. I'm going to need to find f prime at x. I'm going to need to find the derivative, and that is 3x to the second minus 2, right? I'm going to need to find f at, because this is my a and this is my b, I'm going to need to find f at negative 2, and I'll just put that in here, right? What third minus 2 times the what, right? And I'm going to put in here negative 2. Use your brain or your calculator or both, whichever you want. And so we're going to get, and I'm just kind of setting up the things I need. And this is plus 4, right? 2 times 2 is 4 there. So this is negative 4. And then f at 2, I'm just setting up the things I need. I'm going to then plop them into here, right? So this is cubed minus 2 times 2 here. So this is 8 minus 4 is 4. Okay. So f prime at c, right, is f, oh, excuse me, sorry. I was trying to plug in c right in here, right? So this is 3c squared minus 2 equals, and then f at b, I'm going to write this is a and this is b, right? F at 2 is 4, so this is 4 minus, and then a is negative 4, so this is minus negative 4 over, and then this is 2 minus negative 2. So this is 8 over 4, right? This is, if you like, parentheses here. If you like, put parentheses here, right? I like to put parentheses when I substitute. I tell my algebra students to do that. And so this is 8 over 4, which is 2. So this is equal to, that's equal to 2, right? 8 divided by 4. 8 divided by 4 is 2. So I have 3c squared minus 2. I'm trying to solve for c. Add 2, add 2. I get 3c squared equals 4. Divide by 3, divide by 3. C squared equals 4/3. Now I'm going to take the square root of both sides, so I get c equals plus or minus the square root of 4/3. I think you should rationalize, particularly since there's not, you should have a calculator that does that for you, and it makes it better, I think. And so this is plus or minus 2 square roots of 3 over 3. And again, I want to draw what I found here. Remember I'm going to figure out what that is. That's 1.15, and my interval went from -2 to +2, right? And so both of these values are in that interval. So both of these values are my answers, so there's two answers. So I just want to draw real quick what we found. So here we are at -2, and we should be down here at -4. Remember, we found that f at -2 was -4. And remember, f at 2 was +4. So our interval here, 2, +4. And right there is the secant line. So I'm going to draw. Oh, it did ask me to sketch it. I said it didn't ask me to sketch it, but I'm going to anyway. But it did ask me to sketch it, so I'm going to. So there is the secant line. Okay, and then what I want to do is I want to draw the two tangent lines that we found, and they happen at +1.15, so somewhere about here, and it should be parallel. So I'm going to scoot this over there so that I make sure that I make it look parallel. And there is a tangent line. And you notice the slope of the tangent line and the slope of the secant line are the same. And I've done my best to kind of draw it. And you can kind of see that the tangent line, remember, is the slope of the curve at that point. And it certainly looks good. And then here's -1. And here's a wee bit more. And so somewhere right along here, we have another place. And so I'm going to draw here and come over here. So certainly if someone asks you to draw it, you want to make it look like they're parallel lines, because they should be, right? So there's another tangent line. So you had two tangent lines. And notice that, remember, this was approximately equal to ±1.15. And so I just, went a wee bit further than one, there. And I might have needed, maybe I went a wee bit too far, but I tried not to. I tried to be really close. See how close I am right here? Really close. Okay, so we did a lovely job on that. One more here to go on the mean value theorem. So determine whether the mean value theorem applies to the function, and if it does, find the approximate approximate the points that guaranteed to exist by the theorem and sketch the situation. So I have absolute value and in here, and so it is certainly continuous, right? So these are the ifs of the mean value theorem, and absolute value is continuous on negative infinity to positive infinity, so it's certainly continuous. So continuous on 0 to 1, yes, it is. It's piecewise defined, right? And it doesn't, absolute value is piecewise defined, and I mean, I can write it out if you like, but the pieces will both be polynomials, and they meet up with one another. And so what would have to happen is, for it not to be continuous, is if you had something that was piecewise defined and they had a jump in them, but absolute value doesn't have that jump in them, and so that's not a problem. But differentiable is a problem. It's possible that it won't be differentiable. And in fact, I'm going to write this out so that you can see what it would look like. So f of x, if I wrote it out piecewise defined, it's the same, right? That's the top. So this would be 2 minus, and then parentheses, because I'm going to leave it the same, 2x minus 1. Let it be is what I think I said. And the condition for that would be if 2x minus 1, whatever you have on the inside of your absolute value, is greater than or equal to 0, right? And then 2, and then when you go to do your absolute value, you would do the negative of. So this would be subtract from here, and then the negative of 2x plus 1 minus 1. And this is if, I'm writing right on top of my graph there, I know, is less than 0. And so this is 2 minus, so this is minus 2x. And this is a minus times a minus is a plus 1, plus 2 is plus 3. And this is add 1, divide by 2. This is if x is greater than half or equal to half. And then this double negative right here is an add. So this is 2x, right? And then this is minus 1 and 2, this is plus 1. And this is if x is less than half. So you can solve that, add 1 and divide by 2, right? Okay, so that's kind of what we have going. And so you can see that it's continuous because this is continuous everywhere below, above half, right? And including equal to half. And this is continuous because it's just a line below half. And these two are equal at half. So they're going to meet together and fill in the, right, at half. This is equal to negative 1. So this is equal to 2. And this is equal to, at half, is equal to 1. And so it's equal to 2 as well. So they match up right there, right? So when you go to say whether or not it's differentiable, then the slopes would have to be the same at half, right? But when you start talking about differentiable, and I start looking at, so this was f at x, f prime of x is going to be negative 2, right? And this is going to be 2, and this is certainly before half, and this is certainly after. This is before half, that's after half, right? Is the slope. And so what happens right at half is what is the slope there? Well, right at half is where you have that corner happening. And so in order for it to be differentiable, this and this would have to be equal to one another for half, because you'd have to look a little bit before half and a little bit after half. And it's because of the limit definition, right, of the derivative. And so it says that what is the slope, a millimeter before half, because that's your h, your plus h and your minus h, right, on either side of that. Well, my slope on one side is positive, and on the other side, my slope is negative. And so right at half, because right before it and right after it, because remember, my limit gets you the slope on either side of that point, and they're not equal to one another, so my limit doesn't exist. So it's not differentiable, and it's a corner. That's the reason that it's not differentiable at a corner, is because on the limit definition of the derivative, on either side of that corner, the slope is different. And so the limit, either side, because the limit is the slope is the limit, and it's different on either one. And so it fails the differentiable. It's not differentiable at half. They're different from one another at half. So is it differentiable on this interval? It's not differentiable at x equals half. So nope, it doesn't meet the condition. And so we're not guaranteed that someplace in between that the slope is 0, right? Or the slope is equal to, that's what it is. The slope is equal to, the slope of the secant line is equal to the slope of the tangent line. So we're not guaranteed that. So let's look at what the slope of the secant line is. So when x is 0, then we're here. And when x is 3, 1, 2, 3, we're here. And so this is the secant line. And so basically we only have that this is the secant line, and you can see the slope of the secant line. And you can see that the slope of the tangent line, this is just a line. And so everywhere on this line, the slope is the same, and it's not the same as this, right? And everywhere on this line, the slope is the same. The slope is constant on a line, and it's not that. And so anyway, so we made a sketch just to show that, and the derivative doesn't exist here. So the theorem does not apply. Right, it violates 2. The theorem doesn't apply. Okay. Then they show some theorems here, and I think they're kind of intuitive, and I let you investigate them too. We'll be doing that later. Theorem 5 says 0 derivative implies a constant function. And if f is differentiable and f prime of x equals 0 at all points, I think that should have said, of an interval I, then f is a constant function. The f is a constant function. I think it was supposed to be then f is a constant function. I think I tried to type that right out of your book. And so what can you have here that when you take the derivative of it, you get equal to 0 for every value of x. And so if you just kind of think about it, it has to be constant, right? You could put in some things just to see if it would be true. Like if I had 2x, then the derivative would be 2, right? It wouldn't be 0. And so what if I had 2x squared? Then the derivative would be 4x, and there would be a value when it is equal to 0 for x, but it wouldn't certainly be true for every value of x, and that's what it's saying. For every value of x, every point in the interval, it is equal to 0. And this is only one point, right, which is at x is 0, but all other points wouldn't be. And so so it has to be constant, right? So it has to be constant. And that's all that they're saying here. If you want to see the proof of it, I think you can find it online. It's also in your book. Andrea would probably love to do the proof. Functions with equal derivatives differ only by a constant. If two functions have the property that their derivatives are the same for all x on an interval I, then f of x minus g of x equals a constant on I. That is that f and g differ only by a constant. And I just wanted you to think about it. Again, you can go and look at the proof online if you like, and you can also look in your textbook. They prove this if you like. But what, when you take the derivative of it, do you get 6x? Is that right? People are saying, no, that's not right. Right? I did get 6, but 6x squared. So what about this? So is there anything else that you can think of that when you take the derivative of it, you get 6x? All I'm trying to do is to get you to see that it's reasonable what they're saying, right? And so when I take the derivative of 3x squared, I get 6x. What do I have to have so that when I take the derivative of it, I get 2x? 2x is the answer. And would you agree that I could put plus 6 here? because when I take the derivative of 6, I get 0. So you wouldn't know what I had there for sure. So again, with g, take the derivative of it. Well, it has to be 3x squared. It has to be 2x, right? And this could be 7. And so that's all they're saying, is that that if you have two functions that have the same derivative, so this function has this derivative, and this function has this derivative, then it must be that f and g are just different by a constant. So that if you were to subtract f and g from each other, so if you were to take f, 3x squared plus 2x, the way I defined it, plus 6, right? And I was to subtract g, the way I defined it, 3x squared plus 2x plus 7, that the answer would be a constant. And in fact, on this one, the constant that I'm going to get, do you guys agree, is -1 for this value of f and g that I've defined here. So anyway, so it kind of makes sense. Anyway, I thought those were, you can look at the proofs in your book, and if you like, come by my office and we'll talk about it if you like, and look on Khan Academy or other places if you like, and I'll see you in the next video.